Hello everyone. Uh, so today we'll start discussing the topic of shear center, which happens to be the final topic of the end semester portion of our course of Advanced Mechanics of Solids. Now, frankly speaking, this topic is not that advanced. Nevertheless, as we begin learning it, we will note that there will be a few twists and turns along the way about which we should be really careful, and so we should approach this topic with all humility. Because as we learn it, we'll see that we'll have to question how well we have understood some of the basic undergraduate concepts. Now, what we are going to do is not directly go into the definition of the shear center. Rather, we'll start our discussion by falling back on what we had been discussing in the previous two lectures, and then use that as a natural motivation which will help us induce, so to speak, the definition of shear center. So, going back to the previous two lectures, what we were discussing back then was unsymmetrical bending. Now, a very important point to note regarding that discussion, and I had emphasized that a few times during that lecture, during those lectures, was that the entire mathematical framework that we had developed as regards to unsymmetrical bending, it pertained to a case of pure bending. So, So it pertained to the case of pure bending. Now, what do you even mean by that? What do you mean by pure bending? Well, we have to understand that back then, when we derived those formulae for the bending stress and the orientation for the neutral axis through the tan beta expression, we kept on using the variables my and mz to denote the y and the z components of the bending moments. However, those bending moments would actually be induced by the application of some mechanical forces on the beam. So, to take a quick concrete example, suppose we consider a cantilever beam like this, and we consider this kind of tip loading. Now, we understand and know very well from our undergraduate studies that if we take a generic cut section like this, we'll have some kind of bending moment induced here. There'll also be a shear force. Now, from the front view of this diagram, so to speak concretely about the plane, let's orient our x-axis like this, our y-axis like this, so that the z-axis is pointing out of the plane. So the plane that we are talking about here in the bottom diagram, so here we are basically looking at the xy plane. Now, we have to understand that if we go to a different orientation of view, then this picture is not going to look so simple. So, for instance, if we look at the xz plane, then the cross section of the beam will actually come into view. So for example, the cross section in the xz plane, sorry, this will be the yz plane. So let me make that clear. So this will be the yz plane. It may look like a square or a rectangle. It could also look like this kind of a circle. So please understand that this is supposed to be a circle, this one. Or in general, as we had been discussing during unsymmetrical bending, it could take any arbitrary cross section. Now, what is very important to understand is that this force that this transversely oriented force that we are considering here, in this particular orientation of the YZ plane, it may not look necessarily vertically downward, as we had talked about in unsymmetrical bending. However, even if the transverse load, this one, is parallel to the y-axis here, we need to be careful in understanding the situation. So what do I mean by that? So consider this. Suppose we take a circular cross section for the beam and we draw a diagram like this. So this is our wall. And the way that I have drawn this diagram, so this diagram here is exactly this one here, but in a different view. So this force that I have drawn here will be depicted by a force like this. Now the way that I have drawn here, it seems that it is very much passing through the center of this. Okay, now this is the simplest of situations we can think of. However, what could happen is that this particular force is not passing through this center, rather it is a little bit eccentric from the center. Then what could happen? Well, as you can intuitively guess, we could have a situation in that case where this beam not only bends but also twists. So what we mean by that is that this force is going to induce a torsional moment which will have a tendency, which will make this beam to twist around this longitudinal axis. Well, it seems fairly simple to understand, but let us try to probe this idea a bit further. So let's go to the next page and consider this. So let's draw our circular cross section and let us depict, let's draw that again. And let us denote the force like this, which we understand has a line of action which passes through the centroid. Now, the moment we start discussing about the possibility of such a force having a twisting action or a torsion, We know that in this particular case there will be no twisting action, but what are we actually saying in that case? What we are saying is that we are taking the moment of this force here about an axis which is going into the plane and passing through this point. So I repeat, when you are saying that this force has no twisting action or no torsion, what we are basically saying is that this is not contributing to any torsional moment when we consider the moment about an axis which is passing about an axis which is going into the plane and which is passing through this point. But suppose we ask ourselves this question, that instead of an axis which is going into the plane but which does not pass through this point, rather which goes through another point. Suppose we consider an axis like this which goes into the plane but through this point. Then what about the torsional moment contributed by this force? Well, in that case, the torsional moment is not going to be zero. So what I'm saying here is that if we consider the line of action of this will have a non-zero moment arm, which is this distance, and it will definitely induce a non-zero torsional moment. This force will induce a non-zero torsional moment. But then the question arises, just because we are considering such a different axis as this one instead of this one, does it mean that this very same force which was previously not inducing any torsional moment, now it is inducing, it seems to appear some kind of torsional moment as a result of just a different choice of our axis? Is it going to induce some kind of twisting for this beam? The answer, of course, is no. It is exactly the same physical situation. It is only our geometrical choice of the axis which has changed. So that cannot change the physical picture, and therefore even if we consider this axis, there cannot be any possibility of a twisting induced by this force. But then what is happening to the non-zero torsional moment that we are getting when we are considering this axis? Okay, so we'll answer that question as part of our discussion. Next, what we want to do is we will again consider this circular cross section. So it is the exact same circular cross section. Although it looks a little bit different here, but that's just my bad drawing. What we'll do is, instead of a force like this, we are going to apply a force which is a little bit eccentric to begin with. Well, in this case, most of you can intuitively understand that there should be some kind of twisting induced in the beam because of this force. So when we say that, what we are intuitively doing is taking the torsional moment of this force about an axis which is going into the plane and which is passing through this centroid. And that would be absolutely correct, that the torsional moment is indeed non-zero. But suppose I say that, and this is exactly similar to the discussion that we just had as regards to this diagram. So here also what I'll do is I will take another axis which is just to the left of this previous axis, but which is falling in the line of action of this force. So here. So now if we try to take or if we try to find out the torsional moment of this force about this axis, it is certainly going to give us 0 because the moment arm is equal to 0. And again, just like we had asked ourselves in this diagram, that just because we have taken a different sort of axis, does it mean that the result, the apparent result of the torsional moment coming out to be 0 about this means that it is going to be having 0 twisting action here? The answer is certainly not. Just because we have taken a different sort of axis, it's not going to be like that. So there will be a definite twisting in this case, there will be no twisting in this case. So if we focus just on what the torsional moment is as regards to the applied force like this or the applied force like this, but take different choices of the axis about which we are taking the torsional moment, like here, 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 or here, then we see it doesn't give us a very concrete picture. So what exactly is going on? Why are we ending up with this sort of confusion? So it is our aim here to remove this confusion through our discussion of the very basic topic of shear center. So to briefly recap what we have been discussing till now, if we go back to the previous page, we had considered this kind of a transverse force which we understood induce some kind of bending, which we all understand very well. But at the same time, if we look at the YZ plane, which we did here, and we considered this kind of a force which would still look very much vertically downward in the XY plane, but which is clearly off center looking at the YZ plane, we understand that the very same force which was inducing the bending in the previous page here would be inducing, along with the bending moment, some kind of torsion also. So I repeat myself, that when we have a transverse force acting on a beam, then in general that transverse force can induce not only bending but also twisting. So the next question which we ask ourselves is that in the previous two lectures, in the context of unsymmetrical bending, when we kept referring to pure bending, what did we mean? Well, what we meant was that we were considering the kind of applications of forces which would be inducing solely bending and no such twisting. Now you note that we have been having this discussion as regards to transverse forces. It is also possible that we can have forces which are not transverse, rather parallel to the longitudinal axis of the beam, in which case it is very much possible to have not only bending moment but also twisting, but in addition to those two, also axial forces. But for the purpose of our current discussion, we'll be only referring to these kinds of transverse forces where there is a possibility of bending moment as well as a possibility of torsion or twisting. And for the purpose of our discussion of shear center, we will be focusing on the very special case as to when these transverse forces will induce only bending and no twisting. So we write this down. And the important question which we ask is it possible to have a case when the transverse forces induce only bending? So there's a question mark there. Well, it's not really a question, because in the previous two discussions, in the previous two lectures, I had been saying time and again that we are going to consider a case of pure bending. So it is, of course, very much true. The answer is yes. Answer is yes. Definitely it is possible to have a case when the transverse force will induce only bending and no twisting, and that is the case when these transverse forces pass through a very special point, and that point is what is called the shear center. So yes, when the transverse force passes through a special point, called the shear center. So if our transverse force passes through the shear center, there will be no twisting. Okay. Now it will be useful to note down a couple of extremely important points for the shear center. So the first point is that the shear center is a purely geometric entity. Which means that a particular cross section will have a particular shear center that does not change with loading. So if we have a particular cross section, it will have a very definite shear center, no matter what kind of loading we put on it, that is not going to change. Another important point is that even though the shear center is a purely geometric entity which has to do solely with the geometry of the cross section, it is not necessary for the shear center to lie within the cross section. So the shear center need not lie within the cross section, and this will become amply clear as we develop our discussions. Now, with this understanding, we are almost ready to launch into the derivation or to address the question of how we can find out the shear center. And as a first step towards that goal of finding out the shear center for any given cross section, what we'll do is go back and readdress the confusing questions which we had been asking as regards to this circular cross section. So what we were the questions that we were confused about, to quickly repeat myself, is that when we were considering these kinds of transverse forces and we were considering the torsional moments about various axes which were going into the plane, sometimes we found out that it was giving us zero values and sometimes it was giving us non-zero values, but that value coming out as zero or non-zero did not give us a clear-cut idea about whether the beam would actually twist or not. So when we considered this force and considered this axis, we found out quite rightly that there would be no twist. But when we considered this axis, we found out that there would be a non-zero torsional moment, but that did not change the fact that there would still be no twist. Similarly, when we considered this force here and considered this axis, we found out that there would be a non-zero torsional moment, which kind of gave us the correct idea that there would be a twist. But when we considered this axis, we found out there was zero torsional moment, but that gave us the wrong idea that there would be no twist, because there would be very much a twist here. So what is going on here? And what is going on here can be clearly understood if we stop considering this kind of a cross section, rather we consider the beam in its entirety. So that's what we are going to do. So let me go to a new page, and this discussion that we're going to have will not only address those kinds of confusing questions, but it will also give us the recipe to address how to find out the shear center. Okay, so let's redraw that diagram. But this time what we are going to do is we are not going to consider that kind of a simple circular cross section. Rather, what we are going to do is we are going to take some kind of general cross section. So let's take a beam like this. Let's say the beam has this kind of some kind of irregular cross section. Despite what my drawing might indicate, please understand that this is very much a prismatic beam, meaning that whatever the cross section is here at this end, the same cross section is maintained all throughout the length of the beam. I'm stating this fact because this cross section doesn't look exactly like this one, but please pardon my drawing. Okay, so what we understand is that this is a cantilever beam, so there will be a wall here like this, and there will be some kind of transverse force acting on it. Now so let's denote the transverse force before going forward. So let's say it is acting somewhere here. Let's also draw the axis. So let's say this is our x-axis, this is our y-axis, and this is our z-axis. Now previously, when we were considering the circular cross section, which would be a special case of this general cross section, we were only considering the torsional moment that would be induced by this transverse force about an axis which would be either this blue axis or another axis which would be parallel to this axis. So we were considering this axis or something like this, another axis which was like this. Okay. Now the important question which we must or the important point which we must note is that if there is indeed no twisting action induced by this transverse force, then it really should not matter about which axis we are considering the torsional moment. So let me repeat myself. If it is indeed true that this force is not inducing any twisting of the beam, then it really should not matter about which axis we are considering the torsional moment. So how do we reconcile this apparent contradiction? Well, what we are missing in this entire discussion is that when we are considering the possibility of twisting, it should not be we should not be considering this force in isolation. Rather, what we should be doing is we should be considering a cut section of this beam, and then to consider the total torsional moment that is contributed not only by this transverse force but also by the shear stresses which would be exposed on a particular cross section or a cut section. So what do I mean by this? So for that, let me actually take a cut section. So what I'll do is I'll take a cut section here. And this cut section would okay. So this cut section would expose a cross section like this, which would of course be exactly like this because we are considering a beam. Now, if we remove this cut section from there and draw it separately, so what I mean is I draw it separately here. Then the free body diagram for this cutout piece, it would involve this kind of this transverse force definitely, but on the exposed surface, which I will represent by hatch here, which is hidden away behind, on that hatch surface there will be a distribution of stresses which would also be contributing to the torsional moment if we choose to take the torsional moment about any axis. Now please note that this has a direct connection with our undergraduate studies. So no matter which background you come from, whether it is aerospace engineering or mechanical engineering, you have invariably studied in your undergraduate days that when you have this kind of a transverse force, then on any cut section like this, on any exposed surface of a cut section like this, you would have a a shear force. So suppose we were looking at the XY plane, then to repeat our diagram from the first page, it would look something like this, where our transverse force would look like this. So remember that this is in the XY plane. So this is our X and this is our Y, and this is the Z. So we understand that there would be a shear force like this, and of course there would be a bending moment like this. Now coming back to this picture, this hatched part that I have shown here, it would have a distribution of shear stresses in such a fashion that the resultant of those shear stresses in the vertical direction would contribute to this shear force here. I repeat, the distribution of shear stresses on this hatched part would be such that the resultant of that would be contributing to this vertically oriented shear force here, and that in turn is going to balance the effect of this downward pointing externally applied transverse force. So whenever we have this kind of a situation, it is actually the shear stresses and the bending stresses, which you all know very well about, that is what is actually responding to the external load. Okay, and this kind of a shear force is just is like a gross representation of the entire contribution of that distribution of shear stresses. But pertinent to our current discussion of shear center and the twisting action, what we want to say is that when we are going to consider, or when we want to write down or find out the torsional moment of this one, sure, we would be taking it about a certain moment, about a certain axis. So suppose we take it about an axis which is the x-axis itself, or suppose we choose to take it about some other axis which is parallel to the x-axis and which is denoted by x dash. It doesn't matter. We can choose to take the moment, the torsional moment of this externally applied force about any axis, as we had discussed earlier, and we ended up with those confusing questions. But if we have to say anything concretely about the net twisting action that is seen, or the net twist that is seen in this cutaway piece, and consequently in the entire beam that we were considering here, so either you consider this one or this one, so whatever happens here has a direct consequence here. So if we have to consider the twist of this cut piece, then it is not enough to stop at just the consideration of the torsional moment of this one. We have to consider the torsional moment that is contributed by the distribution of shear stresses which is present here, and this is the most fundamental missing link which led to the confusion in the earlier consideration of the circular cross section. So to summarize, what I have been discussing is that it's true that the consideration of torsional moment of this force is going to give either 0 or non-zero values depending on what kind of an axis we are choosing here, whether it is the x-axis or the x-dash axis. But the question of whether this entire thing is undergoing a twist can be answered only when we consider not only the torsional moment of this transverse force, but also the torsional moment that is contributed by the entire distribution of shear stresses which is present on this hatch section. So, tying everything together, if it so happens that this externally applied transverse force indeed passes through the shear center of the cross section, then the whole situation here will be such that the entire distribution of shear stresses here, when we take the torsional moment about an axis, about any axis, it will turn out to be to be such that it balances the torsional moment here. So again, I repeat myself. If it so happens that this transverse force passes through the shear center of the cross section, then no matter what kind of axis we choose to take the torsional moment about, the torsional moment that is contributed by this would be exactly balanced by the torsional moment here. If this transverse force does not pass through the shear center, then the torsional moment of this about any axis would not be balanced by the torsional moment of the distribution of shear stresses about that very same axis. And this is the fundamental important concept of this topic of shear center. So let's write them down quickly. If the transverse force passes through the shear center, then the torsional moment of that force about any axis here I'm not qualifying the definition of any axis because I just had this long discussion. So this any axis would be referring to any of these axis which we understand is going to be perpendicular to the cross section. So this is going to be then the torsional moment about of that force about any axis is going to be balanced contributed by the shear stresses so let's write that as the shear stresses on the hatched part. So when I say hatched part, I basically mean this one. And please note that of course this torsional moment contributed by the shear stresses also has to be computed about the very same axis. Okay, so this is the entire physical understanding behind the shear center and the whole story associated with the possibility of twisting under the action of transverse forces. Now let's come down to the practical aspects of this calculation. You see, we have done this discussion in association with a beam having such an arbitrary cross section, and whatever we have discussed here is going to hold true no matter what kind of a cross section that we have here. But in practice, it is not very easy to find out the distribution of shear stresses given any irregular cross section. So if you have such an irregular cross section, it is not at all easy to find out the distribution of shear stresses here. And if you cannot really find out the distribution of shear stresses here so easily, then how are you going to find out, or how are you going to calculate the torsional moment that we have mentioned here, that is contributed by these shear stresses? So again, talking about the practical aspect of things, it is all right to discuss this thing in a very abstract fashion, but you have to remember that these discussions, they all pertain to structural mechanics, where more than this kind of an irregular section, which may be attractive for a mathematical development, what is really useful, immediately useful, is to consider some practically used cross sections. And this actually ties back to the discussion that we had when we were discussing unsymmetrical bending, where we considered various kinds of cross sections which were unsymmetrical, but which had some great practical importance, like the Z section, the channel section, the C section, the L section, and the I section, or even the T section. So those are the kinds of cross sections which are extremely important for engineering practice, and keeping those in mind, the kind of theory that will develop here will be pertaining to a very important aspect of those kinds of cross sections. And that important aspect is that all of those cross sections, whether it was the Z section, the L section, the T section, the I section, all of them had a characteristic that they were composed of very thin members. So the thickness of the various members which made up those sections was very, very thin. And as long as we have that kind of a thin section or thin members making up the cross section, it is possible to find out some kind of closed form expressions for the shear stresses, and that is what we are going to concentrate on next.